Hi everyone, good morning. In this lecture, we will study normal forms and also type of functional dependencies. So let's start now. So first of all, let me tell you what is the source of this lecture. Uh, what are the standard resources that we are following for this lecture? So we will follow Code's original research paper. Okay. So I told you that this relational algebra was given by Code, right? This we have already seen. This relational model, this relational data model, okay, relational model, or I can say relational data model. So this relational model, this was proposed by Code, this relational model. Okay, so this was proposed by Code. Okay, and one more thing, that actually this Code, he wrote several research papers back to back. Okay, so basically he wrote a series of research papers. He wrote series of research papers. So series of research papers he wrote. In this series of research papers, basically the first paper was about relational algebra, about relational model. The first was about relational model. Okay, so in the first paper, he wrote all about relational model, like everything that we know. Like for example, in relational model, data is represented as a table. Okay, you have rows, you have columns, you have domain, you have key, you have primary key, candidate key, super key. Okay, so all the concepts, the concept of null. So basically, every concept that we have seen in relational model, those concepts were described in this paper. Okay, in the first paper, all the concepts were described, like integrity constraints. Okay, like entity integrity constraint, referential integrity constraint. Okay, domain integrity constraint, key integrity constraint. Okay, so these concepts, all these concepts were described by this code, by Code, in this research paper, in the first research paper. Then in the second research paper, he described some more concepts like normal forms. Okay, so this normal form, this concept was also described. Okay, so like this. So basically, these concepts, like in this paper, he gave the concept of normalization. He gave the concept of 1NF, 2NF, 3NF, 4NF. Sorry, not sorry, 3NF, and okay. So these concepts were given in this research paper. Okay, 1NF, 2NF, 3NF. Okay, these concepts were given. Also in this same research paper, these concepts were also given, like what is a partial dependency, what is a function, transitive dependency. Okay, so what is a transitive FD, what is partial FD. So these concepts were also given. So we will study, so all these concepts we will study now in this lecture. Now let me tell you one thing. So you can notice this was Code's original research paper. So I will give you the screenshot of this paper. Okay, for many concepts, like when we study partial dependency, then I will give you the screenshot of the research paper, original research paper, like where this is defined. Similarly, when we study 2NF, I will give you the screenshot of the research paper where this is defined. Okay, anyway, so now let's move on. So you can notice this is the research paper. This is by Code. This is the original research paper by Code on the normalization. On normalization, this was the paper. Okay, so you can read all the concepts that we have already seen. Like we have seen the concept of functional dependency, right? So this is the functional dependency concept was given by Code. Okay, so this functional dependency concept, it was given by Code in this paper. BCNF was not given in this paper. BCNF was given in another paper. In another paper, BCNF was given in another paper. Okay, so there was another paper for BCNF. Okay, anyway, so there was another paper for BCNF. Okay, anyway, so basically you can notice the concept of functional dependency we have already seen. The concept of trivial dependency, concept of functional dependency. So these definitions, these concepts we have already seen. Now let's move on. For example, this concept we have seen, right? In entity integrity constraint, right? Yes or no? What is entity integrity constraint? Tell me. What is entity integrity constraint? What is that? That is basically that in relational model, every table must have primary key. Yes or no? In relational model, in the relational model, every table, every relation must have primary key, and this primary key cannot be null. Okay, this primary key, so one of the candidate key is chosen as primary key, I told you. Okay, so you can notice for every relation, for each relation, what we do, so here you can notice that for each relation in the database, one of the candidate key we choose as a primary key. And what is the difference? What is the major difference between candidate keys and primary key? What is that? The major difference is that basically this primary key cannot be null. Okay, this primary key cannot be null. You can notice that no tuple is allowed to have undefined value for any primary key component. Okay, no tuple can have null value for no tuple can have null value for any of the primary key attribute. The other attributes can have null value. The other attributes can have null value, but primary key attribute should not have null value. Okay, so you can notice this was given by who gave this concept? Tell me, who gave this? Entity integrity constraint. Who gave this? So okay, code gave this. So you can notice this is the screenshot from the original paper of code. Okay, this is the screenshot from the original paper of code. Okay, about primary key, about entity integrity constraint. So every relation must have primary key, and this primary key is basically one of the candidate key, and this primary key cannot have null value. Okay, very simple. Now let's move on. Now let's so let me tell you in this all the sources of this lecture. In this, for this lecture we will see the, I will put the screenshot of this original paper. You can read, of course. What you can do after the class, you can read those lecture notes. That's what we do, right? Okay, so after the class you can read the lecture notes, and in the lecture notes you can read the screenshot of this code original paper. Also we will follow the Nawate book, the Korth book, and some top university articles. Okay, so this is the source for this lecture. Now let's move. Now why I'm mentioning this a lot of sources, like before starting the lecture, why I'm mentioning this a lot of standard resources? What is the reason? The reason is this, that whatever we study in this lecture, many students, many, actually majority of GATE aspirants, they have misconceptions in many topics in this lecture. Is this clear? So many GATE aspirants, they are learning for the last many years, for the last, I can say maybe 20 years. Okay, so for the last many years, every year GATE aspirants, they are learning wrong concepts, misconceptions. Okay, so in this normalization, so we are going to learn it all, and we are going to learn it the right way. Okay, so basically all these standard resources, from all these recent standard resources we will learn. Okay, so that is the reason I am telling you, before beginning the lecture, I am telling you all the standard resources that we will follow. Okay, is this clear? So before I start this lecture, I want to request you one thing. If you have already studied this normalization concept, if you have already studied 2NF, 3NF, BCNF, from partial dependency, full dependency, transitive dependency, if you have already studied these concepts from some maybe somewhere else, some non-standard resource, then stay ready to forget all those concepts. Okay, so basically keep your mind open, because a lot of your concepts might be wrong. Okay, so we will study all the correct concepts from all these standard resources that I told you. And also, if you are the first timer, if you are learning this normal form 1NF, 2NF, 3NF, BCNF, if you are learning this for the first time, then congratulations. Okay, you are basically you are a lucky person to learn it the right way the first time. Okay, so anyway, because it is very hard for to forget all the wrong concepts and then to learn the right concepts. Okay, it is very hard, like it is not an easy thing, because if some concept you are learning in the wrong way, okay, and you are solving maybe 100 questions, 200 questions using those wrong methods. Okay, using wrong methods you are solving 100 questions, 200 questions, then it will become very hard to understand the concepts in the right way. Okay, because already you are thinking that whatever I know, whatever I understand, that is correct. Okay, so let me tell you that today this lecture will change a lot of your, I can say, perception about these poor resources. Okay, all these resources which do not follow standard resources, there are many coaching institutes, and on the YouTube also you can find, so random teachers you can find. So they don't follow standard resources. They are creating their own concepts. Okay, or maybe they are learning from some poor resources and then they are teaching. Okay, so anyway, something like this happens. I don't know what happens, but whatever we will study, we will follow these books. Okay, let's start now. So let's see the first topic, that is prime attribute. What is a prime attribute? What is non-prime attribute? So the definition is very simple. Then what is a prime attribute? Prime attribute means this attribute appears in at least one candidate key. There can be many candidate key. Yes or no? In your relation, you can have many candidate key. So more than one candidate key, you can have one or more than one. Then in this situation, what is a prime attribute? Prime attribute basically means that an attribute which appears in at least one candidate key. An attribute A is called prime attribute if it is present in at least one candidate key, if it is part of at least one candidate key. And what is non-prime attribute? Non-prime attribute means it is not part of any candidate key. Okay, so this is the definition, very simple definition. You can notice this is the definition from Nawate, that an attribute of relation R is called prime attribute if it is member of some candidate key. Okay, and if it is not member of any candidate key, then it is a non-prime. Okay, non-prime means it is not member of any candidate key. Now let's see some example. Consider this example. Your relation. Okay, so the relation scheme is given to you, or you can call it relation schema. Both are the same words. You can call it relation schema, or you can call it relation scheme. Both are same. So this is a relation which has three attributes. This is the relation schema, and set of functional dependencies is given to you. A determines B, B determines C. Now find prime and non-prime attribute. So tell me what will be the answer. So for prime and non-prime attribute, you must find candidate key, correct? Yes or no? First, you must find candidate key. Agree? So first, you must find candidate keys. Okay, so let's find candidate keys. So here, what will be the candidate keys in this? In this, you can notice A is not on RHS. If you look at all the functional dependency, so in any functional dependency, you can notice this attribute A is not present on RHS, right? So this attribute A is not present on RHS. You can notice since A is not present on RHS of any functional dependency, so we can say that only A can determine A. Only A can determine A. So A must be part of every candidate key. Yes or no? Because no one can determine A. Only A can determine A. Okay, so you can notice A must be part of every candidate key. Now let's check it out. A must be part of every candidate key. Let's check it out. What is the closure of A? What A can determine? So you can notice A can determine A can determine B, A can determine B. Now this B can determine C. Now this B can determine C. So you can notice that this A can determine everything. A plus A can determine everything. Basically, I can say that A can determine the whole relation. Yes or no? I can say that A can determine the whole relation. The whole relation it can determine. So A can determine the whole relation. So A is, so here you can notice, so A is super key. And this is minimal. And this is minimal. So A is primary key. Okay, so A is super key because A can determine the whole relation. So A is super key. And since A is minimal, so A is candidate key. Okay, so A is candidate key. Is this clear to everyone? So you can notice your candidate key is A. Now remember, A must be part of every candidate key. This A must be part of every candidate key. And this A is determining A must be part of every candidate key. And this A can determine the whole relation. So I can say that this A alone is enough. Yes or no? A itself is enough. So I can say the candidate key will be only A. So only one candidate key you have. So tell me what will be the prime attributes? Only one candidate key you have. So what will be prime attributes or key attributes? Another name for prime attribute is key attribute. So you can call it prime attribute. You can call it key attribute. Key attribute means which is part of at least one candidate key. Prime attribute is part of at least one candidate key. So prime attribute will be A. And what will be non-prime attribute? And what will be non-prime attribute? Non-prime attribute will be B, C. So these are the non-prime attribute. Is this clear? Very simple. So prime attribute is part of at least one candidate key. Non-prime attribute is not part of any candidate key. Okay, so this is a simple question. We have done this. Now let's see the next. Tell me about this one. If you have this, relation, if your relation is ABC, and let's assume you have A determines B, B determines C, and C determines A. So tell me, in this relation, like these are the functional dependencies. These are the functional dependencies. Then in this relation, tell me what are the prime attributes, what are the non-prime attributes. So every attribute is a prime attribute because first you find the candidate keys. So you can notice A is also candidate key, B is also candidate key, C is also candidate key. So all of them are candidate keys. So you can notice number of candidate key that is equal to 3. Okay, so all of them are candidate key. Now you can notice what are the prime attributes. So the prime attributes are those attributes which are part of some candidate key. Those attributes which are part of some candidate key. So this is a prime attribute, this is a prime attribute, this is a prime attribute. And what is a non-key attribute, or I can say non-prime attribute? Non-prime attribute, that is nothing. Okay, so nothing is a non-prime attribute. So all are prime attributes. Okay, every attribute is, so basically no non-prime attribute. I can say here no non-prime attribute. There is no non-prime attribute. In this relation, we do not have any non-prime attribute. Okay, so this is a simple idea. What is a prime attribute? What is non-prime attribute? You can notice we can have many different candidate keys. This type of screenshot, whenever you see, these are taken from code paper. Okay, so this type of screenshot are taken from code paper. Is this clear? All this type of screenshot that you will see, these are taken from code's original paper. Okay, this original paper you can find on internet, or you can ask me, I will send you. Okay, so I will upload this, don't worry. But everything that is gate relevant in this paper, I will take. Okay, everything that is gate relevant in this paper, I have already put in the lecture notes. Okay, so anyway, so this is the definition of prime attribute. You can have many candidate keys, you can have several candidate keys. A relation can have more than one candidate key, but you can notice any attribute which is part of at least one candidate key is a prime attribute. All other attributes are non-prime attributes. Okay, now let's move on. Now let's see the concept, the type of functional dependencies: non-trivial functional dependency, partial functional dependency, full functional dependency, and transitive functional dependency. So these concepts we need to see. What is trivial versus non-trivial, what is full versus partial, and what is transitive. So let's start with the trivial versus non-trivial functional dependency. What trivial means in any subject? What trivial means? Hi everyone, am I audible? Is everything fine? Like, can you see the screen? Yuvraj is saying that screen is stuck. Okay, so let's see this. So let's see this one. Can you see the screen? On the screen, you can see this topic, type trivial versus non-trivial. Can you read this? Trivial versus non-trivial. Okay, okay. So now let's see. So what is the trivial? What is, when do we say something is trivial? In any subject, when do we say this something is trivial? When it is always true or it is always false. Either it is always true or it is always false. Okay, so trivial means something which always holds or never holds. Yes or no? Something which always holds, something which always holds or never holds. Yes or no? Something which always holds or never holds. Something which always holds or never holds. So this type of thing, this is called trivial. Trivial means either it will always hold or it will never hold. Is this clear? So this is called trivial. Now you can notice what is a trivial functional dependency. Trivial functional dependency means it will always, it will be present in every relation. Like for example, A can determine A. Yes or no? If I give you the value of A, can you find the value of A? Tell me, if I give you the value of A, can you find the value of A? Of course. Very simple. Now tell me. If I give you the value of AB, can you find the value of A? If I give you the value of AB, if I give you the value of AB, for example, if I give you the value of AB, like if I give you the value of AB, then tell me what is the value of A? Then tell me what is the value of A? What is the value of A? So value of A will be 2, right? Okay, so the value of A will be 2. Very simple. But so you can notice that this AB determines A. This is trivial. This is trivial. Why I am calling it trivial? Because it will hold on every relation. You don't have to apply your brain. You don't need any extra information. This is trivial because it will be applicable. It will be applicable on every relation. In every relation, this will happen. Yes or no? In every relation, you can determine if you have the value of AB, then you can determine the value of A. What about this? If I give you the value of A, then can you find out the value of AB? Then can you find out the value of AB? You need more information, right? Yes or no? You need more information. You need more information, correct? So this is not trivial. So this is non-trivial. This is non-trivial. Is this clear? This is non-trivial because you need more information. So this is not trivial because it will not hold for every relation. A is determining AB. That is not true for every relation. That may be true, may not be true. For some relations, it may be true. For some relations, it may not be true. But this AB determines A. This will be true in every relation. But A determines AB. This may or may not be true depending on the relation. Is this clear? What is a trivial functional dependency? So I can say trivial functional dependency, basically the definition is very simple. The definition is like this, that alpha, anything, alpha implies beta is trivial if and only if alpha is a subset of beta. Sorry, beta is subset of alpha. Okay, beta is subset of alpha. Is this clear? So when I can say that alpha implies beta is a trivial dependency when beta is a subset of alpha. Like I told you, AB determines A. This is trivial. This is a trivial. Okay, like ABC determines AB. This is trivial. Similarly, A determines A. Tell me one very simple thing. Tell me, if you know the value of ABC, can you find the value of AB? If you know the value of ABC, can you find the value of AB? Of course. So this is trivial. Okay, so these are the trivial functional dependencies. Trivial functional dependency means I can say alpha implies beta is trivial. When can I say this is trivial? This is trivial if beta is subset of alpha, or I can say alpha is subset of beta, a superset of beta. Alpha is superset of beta. Okay, is this clear? Now, why do we call them trivial functional dependency? Why we call these trivial? Because they will hold for every relation. Okay, because they are satisfied by all the relations. You can very easily see, because they will always hold for every relation. Okay, so you can very simple this type of functional dependency. If you have a functional dependency where this is LHS, this is RHS, so this is trivial. Remember, this is trivial if LHS is a superset of RHS. LHS is a superset of RHS. Okay, then we call it trivial because it will hold every time. So tell me, trivial dependencies, are they interesting? Can they provide you anything important information? The trivial dependency, the trivial functional dependency, can it provide you any important information about the relation? Any significant information about the relation? Can it provide? No. Why? Because trivial functional dependency is true for all the relations. Yes or no? Whatever relation you take, it is true. Like A determines A, it is true for every relation. AB determines A, that is true for every relation. So trivial functional dependency cannot provide you anything important. Any important information they cannot provide you. So trivial functional dependencies we will never basically consider. Okay, is this clear? So trivial functional dependencies are not important. So trivial functional dependencies are basically unimportant, or I can say not interesting. These are not interesting because they are true for all the relations. So trivial functional dependencies we will not care. Okay, we will not care about the trivial functional dependencies because they will hold for all the relations. Now let's see what is non-trivial. What is a non-trivial functional dependency? If some functional dependency is not trivial, then it is non-trivial. Okay, a functional dependency which is not trivial is a non-trivial. So what is non-trivial functional dependency? Tell me, what is non-trivial functional dependency? What is non-trivial functional dependency? An FD, a functional dependency which is not trivial, which is not trivial. A functional dependency which is not trivial. Very simple. Okay, very simple. So you can notice this is the definition of non-trivial functional dependency. A functional dependency which is not trivial. Okay. Now you can notice. So these are the non-trivial functional dependencies. I will write this non-trivial functional dependency. In short, I will write like this. Okay. NTFD. Is this clear? I will write like this. Non-trivial functional dependency. So like for example, if you have a relation, let's assume you have a relation A, B, C, D. And in this relation, if I give you this functional dependency, like AB determines C, then you can notice this is not trivial, right? Yes or no? In this relation, I can also give you trivial functional dependencies. Like if you want, these are the trivial functional dependencies. So what are trivial functional dependencies? For example, A determines A. For example, D determines D. For example, DC determines C. Okay, for example, AD determines A. So these are trivial. All these are trivial functional dependencies. Now, what is non-trivial? You can notice this is non-trivial functional dependency. For example, what about AB determines BD? What about this? Is this trivial? Is this trivial? Is this trivial? So this is not trivial. This is non-trivial functional dependency. Okay, what about AB determines BCD? What about this? AB determines BCD. This is also not trivial. So this is non-trivial functional dependency. Okay, A determines B. This is non-trivial. A determines ABCD. This is non-trivial. So these functional dependencies, these are non-trivial functional dependencies. Is that clear? So these are your non-trivial FDs. Okay, so very easy. Now let me tell you that, can you notice one thing? Look at this non-trivial functional dependency. Look at this non-trivial functional dependency, like AB determining BC. Look at this non-trivial functional dependency. Look at this. Observe this. Okay. So you can notice this contains two. Can I split this? You know the split rule. Yes or no? You know the split rule of. You know this. We already know this. The split rule, split and combine rule. So split rule of split/combine rule. On RHS. Rule on RHS of FDs. For functional dependencies on RHS, you can split also, you can combine also. On RHS. Remember, on RHS, you can split also, you can combine also. So for example, if you have A goes to BC, then this is same as, remember, this is same as two things. Okay, A determines B, A determines D. Is that clear? So okay, so remember, you can combine also. You on the RHS you can combine also, and you can split also on the RHS. So this is your split rule. Now anyway, let's see here. So look at this non-trivial functional dependency. If you notice, this is okay, I can write it like this. It is basically saying that AB can determine B, and AB can determine C, and AB can determine C. Yes or no? Now you can notice this is trivial, right? This is the trivial uninteresting. This is not interesting part. This is the trivial FD. Or I can say this is the trivial part of this FD. Yes or no? This is the trivial part of this FD. Let's call it, for example, FD1. So I can say this is trivial part of FD1. Trivial part of FD1. Is this clear? Trivial part of FD1. Yes or no? and this is the non-trivial part, and this is the non-trivial part of FD1. This part is non-trivial part of FD1. It is making this non-trivial. This part is making it non-trivial, but you can notice that this is the trivial part of FD1 and this is the non-trivial part of FD1. So you can notice this is not interesting, right? Yes or no? This part is not interesting. This part is not interesting, but this part is interesting. This part is interesting. So you can notice that whenever you have this type of situation, whenever you have in any non-trivial functional dependency, if you have this type of situation, like alpha, like for example, alpha A determines A beta. If you have this type of situation, if you have this type of non-trivial functional dependency, then tell me which is interesting here. If you have this type of non-trivial functional dependency, then you can just consider this. You can just consider this, because okay, this will happen, right? Correct? Yes or no? This functional dependency will imply this, and this functional dependency will imply this. Sorry, alpha A determines beta. Sorry, alpha A determines beta. Okay, so you can notice this functional dependency determines this, and this functional dependency determines this. Is this clear? So basically, you can remove this part which is on LHS, this part of RHS which is already on LHS. This part you can remove. Is this clear? Tell me, is this clear? So this part of RHS which is already on LHS, this you can remove, because if you notice, this is uninteresting. Alpha A goes to A. This is trivial. Okay, this is trivial. So we will only consider this. So this type of non-trivial functional dependency we will consider. And actually there are some authors who define like this. Let me tell you, there are some authors, and because of this reason, because of the same reason, can you notice that these two, can I tell me one thing? If I have non-trivial functional dependency like this, for example, if I have this type of non-trivial functional dependency, A goes to B, A determines B, then this type of non-trivial functional dependency you can easily write like this, that AB determines, I can say A determines AB. Yes or no? You can easily write like this, A determines AB. Because if A can determine B, then A can determine AB, because A already determines A. This also we know. Okay, so this split rule we know. Also, another rule we know. What is that? Another rule, that is basically, if alpha can determine beta, then alpha Z can determine beta. If alpha can determine beta, remember, it's like if alpha can beat beta. Okay, if alpha can beat beta, then alpha Z, of course, alpha Z with additional power, of course, you can beat. Yes or no? Very simple. So this, if alpha can determine beta, then alpha Z also can determine beta. But this is not true. This is not true, right? This is not true. Okay, this is not true. So but this is true. But this is true, that if alpha can beat beta, if alpha can determine beta, then I can say that alpha can determine alpha beta. Yes or no? This I can say. I can say that if alpha can determine beta, then I can say alpha can determine alpha beta. For example, if alpha can determine B, for example, if A can determine B, then this is trivial. Okay, then this is trivial. A can determine A. This is trivial. So from these two, I can say that A can determine AB. Okay, this is trivial. So you can notice alpha, if alpha can determine beta, then I can say alpha can determine alpha beta. Okay, so, and this is your, you can also go in this direction. You can also go in this direction. By the split rule, you can also go in this direction. Okay, anyway, so very simple point that, so if you have non-trivial functional dependency like this, then you can also write like this. And if your non-trivial functional dependency like this, you can also write like this. Agree? Did you notice that? Okay, so this type of, so if you have this type of thing, for example, if you have A, B, C determining C, D, E, if you have A, B, C determining C, D, E, then I can write it A, B, C determining D, E. Yes or no? If you have A, B, C determining C, D, E, then this is trivial part. This part is trivial. I can say this part is trivial. This part is trivial. Yes or no? This part is trivial. So you can remove this part. So you can notice this is a two-way. Okay, very simple. So that is the reason I am saying that you can define non-trivial functional dependency like this, or you can define non-trivial functional dependency like this. Both are equivalent definitions. Is this clear? So you can define, like some authors, the definition of non-trivial functional dependency. You can define it anyway because both the definitions are equivalent. Non-trivial functional dependency. So let's see the definition one. Definition one. What is the definition one? Anything that is not trivial. Yes or no? Anything that is not trivial. So like for example, I can say alpha determines beta is non-trivial. Is non-trivial. If and only if I can say that alpha is not a superset of beta. Alpha is not a superset of beta. Means it is not trivial. So definition one says that just that it is not trivial. Yes or no? So definition one says that non-trivial means not trivial. So definition says that not trivial. It simply means that it is not trivial. Okay. And what is definition two? What is definition two? In the definition two, basically what you can do, basically you can, if something is common, LHS, RHS, if they have something common, then you can remove that common part from the RHS. Yes or no? If you have something common, LHS, RHS, if they have something common, then you can remove that common part from the RHS. Like here, they have something common. You can remove this common part from the RHS. Is this clear? So like you can notice, you can make this note that in any non-trivial, in any functional dependency, in any functional, or I can say non-trivial functional dependency, in any non-trivial functional dependency, okay, if something is common, like for example, let's assume Z is equal to, LHS intersection RHS. Means this Z is what? This is the common part of, this is the common part on, this is the common part on LHS, RHS of FD. Okay. So if this is the common part, then what we can do, then this common part can be removed from the RHS. Can be removed. Yes or no? Then it can be removed from RHS. So this is what I'm saying. Is this clear? So basically I'm saying that if you have this type of FD, like alpha Z determines Z beta, okay, if you have this type of functional dependency, then this common part you can remove on RHS. From RHS you can remove. From RHS you can remove this common part. You can remove this common part from the RHS. You can remove this common part from the RHS. Okay. So you will get an equivalent functional dependency. So these are equivalent. This is equivalent, this is equivalent. So this is the definition two. Definition two simply says that basically nothing common. Alpha implies beta is non-trivial functional dependency. It is non-trivial functional dependency if and only if, first of all, if and only if, very simple, if and only if alpha intersection beta is 5. Is this clear? They have nothing common. So alpha determines beta. This is non-trivial functional dependency. This is non-trivial if they have nothing common. Alpha intersection beta, they have nothing common. And tell me, the definition one, is this equivalent to definition two? Definition one, is this equivalent to definition two? Yes, they are equivalent. Definition 1, definition 2, they are equivalent. Okay, because if you have something common, you can remove from the RHS. This is what we have seen. If something is common, then you can remove that from the RHS. Like here, if this Z is common, you can remove this Z from the RHS. This Z you can remove from the RHS. Okay. So is this clear? The definition, two definitions, any of them you can use. There is no problem. There is no problem. Okay. Any of them you can use. Now, what we are going to consider? We are going to consider basically, if you look at all the non-trivial, so what we will consider? We will consider non-trivial functional dependency, also RHS containing only single attribute. From now onwards, what we will consider? Because if you have this type of, basically now onwards, what we will consider? For all the concepts, what we will consider in all the concepts? Consider in all the concepts that we study in normal forms, or I can say in normal form concepts. So this concept that we are going to see in normal form concepts, what we will consider? We will consider only, will we consider trivial functional dependency? Trivial functional dependency is not interesting. That will hold for every relation. So what we will consider? We will consider non-trivial functional dependency first of all. First of all, we will consider non-trivial functional dependency. Okay, remember, we will consider non-trivial functional dependencies. And second, these non-trivial functional dependencies, only those, basically, we will split this non-trivial functional dependency so that RHS has only single attribute. Okay. Non-trivial functional dependencies with RHS containing single attribute. Okay, is this clear? So we will consider only non-trivial functional dependencies with RHS having single attribute. What if RHS have multiple attributes? What if RHS have multiple attributes? Like if RHS has multiple attributes, then you can split. Okay, then you can split. You can split. A goes to A determines B, A determines C. So these we will consider. Is this clear? We will consider these. These we will consider. Is this point clear to everyone? Like if you have A, B, C determines D, E, then what I will consider? Basically, if you have this, then what I will do? Then I will do A, B, C determines D, A, B, C determines E. So basically, on the RHS, we should have single attribute. So this type of non-trivial functional dependency we will consider. Is this point clear? What we will consider? We will consider non-trivial functional dependency. We will consider with RHS having single attribute. With RHS having single attribute. If RHS does not have single attribute, you can split. Okay? Tell me, is this clear to everyone? So we will consider non-trivial functional dependencies with RHS containing single attribute. If RHS does not have single attribute, we will split. In all the concepts that we study, like we study partial dependency, functional transitive dependency, 2NF, 3NF, BCNF, all the concepts that we study. In all the concepts, we will consider the non-trivial functional dependencies where RHS has a single attribute. Okay, where RHS has single attribute. Non-trivial functional dependency with RHS containing single attribute. Because remember, trivial functional dependency, they will not change anything. Okay, like trivial functional dependency will hold for every relation. Every relation contains trivial functional dependencies. So trivial functional dependency cannot change anything, cannot affect anything. Okay, cannot affect the answer, cannot affect the, I can say, the properties of the relation, because trivial functional dependency will hold for every relation. So those are not interesting. So what we will do? We will consider only non-trivial functional dependency. Okay, with RHS having single attribute. If RHS does not have single attribute, then we can split. Okay, now let's move on. Now let's see the next concept, that is partial functional dependency as full functional dependency. And this is very intuitive concept, let me tell you. partial functional dependency, partially dependent and fully dependent, partially dependent and fully dependent. Okay, so for example, this is a very intuitive concept. Let's understand this intuitively. Like, what is fully dependent? Fully dependent, like for example, if I say that this person, let's assume if I say that this person A is fully dependent on B comma C. Okay, let's assume this is a children, let's assume this is a child, let's assume this is a child. Okay, so this is your like for example, let's assume this is a child. If this is fully dependent on, if this is fully dependent on person B comma C, then what it means? Tell me what it means. Then can I say B can determine, can I say then, okay, it is fully dependent on them. Remember, it is fully dependent on person B comma C. Then what it means? It means that B comma C, they will determine A. And can B determine A? Can alone B determine A? Alone B cannot determine, because this is fully dependent on person B comma C. It is fully dependent on B comma C. So you can notice BC will determine A, B cannot determine A, B cannot determine A, and C cannot determine A. Is this point clear? What fully dependent means? What fully dependent means? Fully dependent, for example, here I can say that A is fully dependent on BC. Here basically, here I can say that A is fully dependent on BC. If this type of situation happens, then I can say that A is fully dependent on B comma C, or I can say BC, not B comma C. It is fully dependent on BC. Okay. So anyway, this is just analogy thing. Like, this is just an analogy. This is not the concept. This is just the analogy. Now let's see the definition. The definition is very simple. What is fully functional dependency? Fully functionally dependent. Fully functional dependent. Fully functionally dependent. We can call it full FD. Full functional dependency. So when can I say? Like, very simple definition. I can say that this alpha determines beta. This is full dependency. It is a full dependency. It is like, okay, like this beta is fully dependent on alpha. This beta is fully dependent on alpha if and only if, okay, if you remove something from alpha, if and only if you remove something from alpha, like alpha minus A, if you remove something from alpha, then what will happen? Then it will not determine B. Yes or no? Okay, for all A belonging to alpha, what I can say? I can say that if you remove something from alpha, it will not determine beta. Is this clear? Tell me, anyone has any doubt? It will not determine beta. It will not determine beta. Like, if you remove something from alpha, then it will not determine beta. Okay, the same definition in another words. What I can say? I can say that. So the same definition, is this clear? Tell me. Anyway, the same definition, I can say that beta is fully dependent on alpha. This is full dependency. Okay, this is full dependency. What that means? This is full dependency. What that means? That means beta is fully dependent on alpha. It is fully dependent on alpha. It is fully dependent on alpha if and only if subset of alpha, proper subset of alpha cannot determine beta. If and only if proper subset of alpha cannot determine beta. Is this clear? Cannot determine beta. So if and only if any proper subset of alpha, if you take some proper subset of alpha that cannot determine beta, So we can say that this beta is fully dependent on alpha. Is this clear? Tell me, beta is fully dependent. Beta is fully dependent if and only if you take proper subset of alpha, whatever proper subset you take, then it cannot determine beta. So I can say that for all a belonging to alpha, I can say that if you remove this a from alpha, then you cannot determine beta. So this alpha minus a cannot determine beta. So this is the definition of fully functional dependency. And what is the partial functional dependency? The same way, what is the partial functional dependency? What you will say that what is the definition of partial functional dependency? Partial FD. What is that? I can say that this is partially dependent. I can say alpha is partially dependent on beta if there exists something you can remove from alpha. If there exists something on alpha such that you can remove for some, yes, some a you can remove, and you can still some a you can remove, something you can remove from here, you can still determine beta. Is this clear? Basically, now this is very intuitive. This is very intuitive that if you can, for example, if something you can remove and still you can determine beta, then I can say beta is partially dependent on alpha. Yes or no? Tell me yes or no. So very simple, this partial functional dependency, this partial FD, I am saying that this alpha, or I can say beta, is partially dependent. When I say that alpha implies beta is partial FD, what it means? It is partial FD. What it means? It means beta is partially dependent on alpha. It is partially dependent on alpha. Okay. If and only if some subset of alpha, some proper subset of alpha can determine beta. Some proper subset of alpha itself can determine beta. So you don't need the entire beta. So you don't need the entire alpha. Is this clear? You don't need the entire alpha. Is this clear? You don't need the entire alpha. Basically, this is partial because you don't need entire alpha. This is partial because you don't need entire alpha. Is this clear? So some proper subset of alpha itself can determine beta. So you don't need entire alpha. Here you need entire alpha. In the full functional dependency, you need entire alpha. Using diagram, let's try to understand. Before that, let's take this example. Consider this example. You have a relation A, B, C, D, E, and these are the functional dependencies. Tell me in the definition, before we see this, tell me in the definition, whatever definition we have seen, did we use the word candidate key? In the definition, did we use the word candidate key? In the definition of partial functional dependency and full functional dependency, did we use the word candidate key? I did not use. So tell me, if I ask you this question, tell me, like for example, my question, some questions I am asking you. Okay, back to back, some questions I am asking you. First question, is CD determines E a partial dependency? Is this a partial dependency? CD determines E. Is this partial? Is this partial? CD determines E. Is this partial? Is this partial? What is the definition? When it will be partial? Just tell me. When it will be partial? When it will be partial? Arey, just tell me when it will be partial. It will be partial when C can determine E or D can determine E. So check can C determine E? Check C plus. Check C plus. What is C plus? What is closure of C? That is C. What is D plus? What is D plus? D can determine D. D can determine A. A can determine E. So tell me, can I say D determines E? So you can notice D determines E, right? So you can notice D determines E. So is this partial? Is this partial? Yes. Why? Because you don't need the entire CD. Because you don't need entire CD. Yes or no? This is partial because you don't need entire CD to determine E. Is this clear? So this is partial because you don't need entire CD to determine E. So this is partial because D can determine E. So remember, this is partial FD. Is this clear? This is partial FD. Is this clear to everyone? So this is partial. Tell me. What about D? What about D determines E? What about this one? What about this one? D determines E. Is this partial? Is this partial? This is full functional dependency. This is full functional dependency. Why? Because you cannot remove anything from LHS. Okay, why? Because you cannot remove anything from LHS. Because we cannot remove anything from LHS. Okay, we cannot remove anything from LHS. Is this clear? Because it is a single attribute, you cannot remove anything from LHS. Okay, so like this. What about next question? What about this? For example, BD determines C. Is this partial or full? BD determines C. Is this partial or full? Is this partial or full? This is not even a functional dependency. It is not even a valid functional dependency. It is not even a valid functional dependency. Is partial or full FD? It is not even valid functional dependency. It does not, okay, it is not a FD on this relation. It is not a valid FD on this relation. Is this clear? It is not a valid FD on relation R. Because if you find what is BD plus, if you find what is closure of BD, BD can determine BD. BD can determine BD. D can determine A. This D can determine A. A can determine E. Okay, so like this. So you can notice this BD cannot determine C. Anyway, so this is the concept. Is this concept clear? Tell me. So like this, you can check it out. Okay. Anyway, this is the candidate key. If you want to find the candidate key, how will you find? Tell me, how will you find the candidate key? How will you find the candidate key? You can notice this BCD, these attributes do not appear on RHS. So they must be part of every candidate key. Correct? You can notice B, okay, to find CK, to find candidate key, you can notice that attribute B, C, D are not on RHS. Yes or no? Are not on RHS of any FD, of any non-trivial FD, of any non-trivial FD. So they must be part of every candidate key. So they must be part of every candidate key. So you can notice BCD must be part of every candidate key. Yes or no? It must be part of every candidate key. And you can notice this is alone. This alone is itself. Alone is enough. So this BCD, this alone is enough. Now let's move on. So what is the definition of this functional dependency? Fully functional dependency definition we have seen. Partial dependency definition we have seen. You can check it out from the Navate. This is Navate. You can check it out. Okay. So these definitions we have seen. These slides you can read. And this is your original code paper. This is the original paper of code. I told you this type of screenshot. These are from the original paper of code. Now let's see this example. And this is the example given in this code paper. In the paper of code, this example is also given. Okay, let's see this example. So in this question, what the question is asking. So like, for example, let me ask you something like this. Tell me, So this is the given. These are the given functional dependencies. These are the given functional dependencies. What this means? Tell me what this means. What this means? Like when I say like this, see, if I say like this, alpha, if I say like this, what this means? This means that A can determine B and B can determine A. Okay, what this means? Remember, this means that A can determine B can determine A. Is this clear? So this means A can determine B can determine A. Okay, this is the idea. So if I say like, and this is the original paper of code, remember. This is the original paper of code, and this example is given in this paper. Anyway, so you cannot, this means that A determines B and B determines A. Okay, so here what this means actually, if you notice, so let me tell you what this means. So actually these FDs, if you notice, these FDs, what they mean, these FDs, if you notice, these are basically like ABC is determining DE and DE is determining ABC. Okay, is this clear? ABC is determining DE and DE is determining ABC. Also DE determines F. DE determines F. Okay. Also, AB determines D. Also, E determines C. Okay, so these are the functional dependencies. Okay, this is your relation. So you can clearly see your relation has these attributes. Your relation has A, B, C, D, E, F. These are the attributes on your relation, and these are the functional dependencies. Okay, now my first question, DE determines C. Is this full dependency or partial dependency? DE determines C. DE determines C. Is this full dependency or is this valid dependency? First of all, DE determines C. Is this valid functional dependency? Is this valid functional dependency? Check it out. Just check it out. Just check it out. Just check it out. What is D plus? D plus means it will determine DE. DE can determine F. DE can determine F. DE can determine ABC. DE can determine ABC. Okay, DE can determine ABC. So ABC, DEF, everything. So okay, now tell me, is this partial or full? Is this full FD or partial FD? Is this full FD or partial FD? Can you remove something? Can you remove something? Tell me. Can you remove something? Just tell me this point. Simple point. This is partial. Why this is partial? This is partial FD. This is partial FD. Why? Because you don't need DE. You don't need this DE. Yes or no? This E is enough. Yes or no? This E is enough. You don't need DE. So remember, this is partial. Remember, this is partial FD. Is this partial FD? Is this partial FD? Is this partial FD? This is not partial. This is full. Okay, is this clear to everyone? So for example, this E goes to C. The E goes to C is full. Is full or partial? It is full. It is full, right? You cannot remove anything. It is full. This functional dependency is full. This is full functional dependency. You cannot remove anything from the LHS. So this is full functional dependency. Let's see the next example. ABC determining DE. What about this one? ABC determining DE. What about that? ABC determining DE. What about this? ABC determining DE. Is this full or partial? Sorry, D. ABC determining D. Is this full or partial? So this is also partial. This is also partial. Why? Because you can notice AB itself can determine D. Because AB is enough. Yes or no? Because AB is enough. Because AB is enough. So this is partial functional dependency because you don't need the entire LHS. So the definition of partial dependency, functional dependency, is this clear? What is partial and what is full functional dependency? So you can notice, if you have this type of situation, AB determines C, A determines C, then what will happen? If you have this type of situation, so basically if AB is determining C and also A is determining C, then which of them is partial? Which of them is partial? AB determining C. Okay, if this, then which of them is partial? Which of these is partial? So which of these is partial? And the answer is very simple. This is partial. So remember, this is partial FD, because you don't need the entire AB. Is this clear? This is full. You need the entire A. You need entire LHS. Here you don't need entire LHS. Okay. So here you can notice AB determines C, A determines C. Then this AB determines C is partial. I can say C is partially dependent on AB. Okay. So this is the idea. Now, what about this one? If there is a dependency, C determines E. Then what can you say about this one? BC determining E. This is partial, right? If C can determine E, then BC determining E is partial. Okay, so this is the definition anyway. Now let's move on. Before we move on, let's see the diagram. So let's see the diagram. Let's understand this concept by diagram. So remember, this is the conclusion. I can say this is the conclusion. So what is the conclusion? The conclusion is very simple, that I can say that this XA determining B, okay, is partial. Basically, I am saying that this is partial, means if you have like this X determining A is partial. When can I say this is partial? If this is your X, let's assume this is the X. Now X is determining A. When can I say this is partial? When some subset is determining A. Yes or no? When some subset is determining A. Yes or no? In this situation, I can say that this X determines A. This is partial FD. Is this clear? Where Y is a proper subset of X. Okay, so very simple. This is the definition of partial functional dependency. And what about the fully functional dependency? What about the full functional dependency? When can I say this is full? When this can never happen. Full means this can never happen. Subset can never determine it. Okay, is this clear? Then we call it full functional dependency. So very simple, right? So these concepts we have seen. Now let's see the next concept, that is transitive functional dependency. What is this concept? Let's understand. Okay, so let's understand this transitive functional dependency. Tell me, did you understand partial and full functional dependency? Did you understand partial dependency, full functional dependency? Did you understand the difference? Okay, very clear. Also remember, only consider non-trivial functional dependency. Okay, only consider non-trivial functional dependencies, because trivial functional dependencies, they will hold on every relation. Trivial functional dependency cannot decide anything. Trivial functional dependency cannot do anything, basically cannot do anything significant. Okay, anyway, now let's see transitive functional dependency. So what is the definition of transitive functional dependency? Let's see the definition from Korth. This is the book database from Korth. Okay, so in this definition is given. What the definition is saying, that if you have, okay, first you understand the definition. Anyway, let me explain this definition. Alpha comma beta, these are set of attributes such that alpha implies beta, beta does not imply alpha, and beta implies A, then A is transitively dependent on alpha. Anyway, let's explain this definition. Let me explain. First of all, what is transitive? When you see this word transitive, what comes to your mind? When you see this word transitive, what comes to your mind? Whenever you see this word transitive, it comes to your mind, right? Like something is something is implying something, and this is implying this, then this is transitive. This is called transitive. This is called transitive. Yes or no? Is this clear? So whenever you see transitive word, whenever you see the word transitive, then what will come to your mind? This will come to your mind. Like X can determine Y can determine Z. Okay, so this X determining Z, this is transitive. So what is transitive? Is this transitive? Tell me, is this transitive? No, this is transitive. X determining Z, this is transitive. Okay, so this is the general transitivity in general. This is what we call transitivity in general. In general sense, this is the transitive. In general sense. Okay, now let's see the definition of transitive FD. Let's see the definition of transitive FD. Transitive functional dependency. What is the transitive functional dependency? So we can say that, I'm saying that X determining A. Okay, remember I told you we will consider only single attribute. So X determining A, is it transitive? When can I say this is transitive? Tell me. When can I say this is transitive FD? This FD is transitive FD. When can I say this FD is transitive FD? This FD is transitive FD if there exists something, some middleman exists. Some middleman exists. There exists some middleman. There exists some middleman such that X is determining Y is determining A. Correct? Is this clear? Tell me, is this clear? There exists some middleman. There exists some middleman such that X is determining Y is determining A. Okay. The only one extra condition is there. One extra, the last condition. This is the extra condition that Y should not determine X. Y should not determine X. This is the only additional condition. Okay. So tell me, is this clear? What is the transitive functional dependency definition? Tell me, is this point clear? Transitive functional dependency definition. Very simple definition that. Very simple definition. X determining A is a transitive FD. When can I say this is transitive FD? Like X determining Z. X determining Z. When can I say this is transitive? This is transitive if there is a middleman. If there is a middleman. Okay. If there is a middleman. So you can notice this is the definition. Now Nikhil is asking, can A determine X? You tell me, Nikhil, you tell me. Can A determine X? This is the complete definition. This is the complete definition. This is the complete definition. Okay. Now. Can A determine X? Some observation. Some observations. Can A determine X? Okay, tell me, can A determine X? Like if X is determining Y is determining A, Y is not determining X, Y is not determining X, then can A determine X? Anyone? Can A determine X? If this situation happens, can A determine X? Why? Can anyone prove it? The answer will be no. The answer will be no, never. Can anyone prove it? Can anyone prove it? Very simple. If contradiction, by contradiction. Yes, very good. By contradiction. By contradiction, you can prove. By contradiction, you can prove. If A determines X, and we already know Y is determining A. We know Y is determining A is determining X. then y determines x. That is the contradiction. I told you that y should not determine x. That is the contradiction. Is this clear? Tell me, is this point clear? Let me know. Okay, very simple. So it cannot happen. But remember, this is not part of the definition. This is not part of the definition. Is this clear? So this is not part of the definition, because this is I can say from this definition you can imply this. Correct or not? Is this clear? From this definition you can imply this. Just wait. Ekta Mahavit, just wait. Okay, is this clear? This is the complete definition. Is this clear? Tell me, did you understand transitive definition, transitive FD definition? Let's take example. With example, this concept will become more clear. So remember okay, again I am telling you the transitive, transitive FD definition. Transitive FD definition. So the transitive FD definition is very simple. Now I am saying that alpha determines A. This A is a single attribute. Remember this A is a single attribute. Is this clear? Here this A is a single attribute. Whenever I write like this is a convention I am using. Okay, remember this is a convention I am using. What convention I am using? That if I write like this, A, B, C, if I write like this, then what they mean? They mean single attributes. Okay, they mean single attributes. Single attributes. Okay, individual attributes. And when I write like this, alpha, beta, x, y, if I write like this, then what it means? Alpha, beta, x, y, gamma, z. If I write like this, then they mean set of attributes. Okay, they mean set of attributes. They can be single also. Can be single also. But these are set of attributes. Is this clear? This convention, tell me, is this convention clear? So now let's move on. Now you can notice that alpha goes to A. Alpha goes to A is transitive. Is it transitive? When can I say alpha goes to A is transitive? Alpha goes to A is transitive if there exists a middleman. If there exists a middleman. If there exists a beta. If there exists a middleman. Okay. If there exists a beta such that this will happen. Okay. And also this should not happen. The only additional condition is this should not happen. This should not happen. In this situation, if this happens, then okay, then alpha determines A is a transitive dependency. Is a transitive functional dependency. Okay, is this clear? It's transitive functional dependency. This T means transitive. Okay, so this is the complete definition. And of course, tell me, A cannot determine alpha, right? This we have seen. But should I write this? This is redundant. Can you notice? Should I check this? Tell me, should I check this? No, this is redundant. Because if this happens, tell me, remember, if this happens, then this will also happen. So this is redundant. Okay, anyway, let's move on. Let's see some examples. So you can notice this screenshot is taken from whom? This is a screenshot taken from your code's original paper. This is the screenshot. So you can notice this is the definition given. Transitive dependency definition is given. Okay, this is what we have seen. Consider this example. Again, you have a relation A, B, C. And let's assume A is determining C. Let's assume A is determining C. Okay. In this situation, this is my question. A is determining C. This is the FD. And my question is AB determining C a transitive dependency? Is that a transitive dependency? Is AB determining C a transitive dependency? I'm asking for this. Is this a transitive dependency? So the answer is yes. The answer is yes, because there exists some middleman, right? Okay, so this AB determines C. This is transitive. This is transitive because you cannot, this does not determine this. You cannot, this does not determine this. Okay, so everything is fine, right? Okay, everything is picture perfect. Everything is picture perfect. So I can say, so what we can say? So we can say AB determines C is transitive dependency. Okay, can you notice this is a partial dependency also? Can you notice this is partial dependency also? This AB determines C, this is partial dependency also. This is partial FD also. Okay, so anyway, so this is the idea. What about A determining C? What about A determining C? A determining C, is it transitive? Can I say this is transitive functional dependency? Can I say this is transitive functional dependency? The answer is no. There is no middleman. A determines C, there is no middleman. Is there anyone? Is there anyone such that this picture will happen? Is there anyone such that this picture will happen? Is there anyone such that this picture will happen? Also here, one more thing I want to tell you. Here in the definition, one more thing I want to tell you. In the definition, this A must not be part of X comma Y. Okay, in this one more thing, one more note. This A is not part, because we are considering the non-trivial FDs. One more thing, actually it is part of the definition. You can notice this. Read this. It is not alpha, it is not in beta. Okay, so this is from the course. This is from the book course. So what I'm saying that here, I'm saying that here also A does not belong to X. Okay, A does not belong to Y. Is this point clear? And A is a single attribute. A is a single attribute. A does not belong to X. A does not belong to Y. Is this point clear? Tell me. A does not belong to X. A does not belong to Y. It is a single attribute. It is a single attribute. And also A does not belong to X. A does not belong to Y. A does not belong to alpha. A does not belong to beta. Tell me, is this point clear? Okay. So like this. Now you can notice. Now tell me. Now tell me. So basically you cannot take this. Can I take this? A determines C. The picture is perfect. This is picture perfect. This is picture perfect. Can I do this? Can I do this? Can I do this? C is part of this. C is part of this. So this you should not do. So this you should not do. Why? Why you should not do this? Because remember, because this should not happen. This C must not. Okay, if I consider this, if I consider this beta, then C should not belong to beta. Yes or no? C should not belong to beta. Okay, so this is the idea. I hope this point is clear. So remember, this is not a transitive functional dependency. Okay, now let's see some more questions. One more example let me take. Let's assume A, B, C, D, and yes, these are the yes, these are the by definition, Mavit. Like these definitions are given by code. These definitions are given by code. we are using them. Okay. And remember why these definitions were given by code. Like why code gave these definitions. He must have done some research. He must have done some research. He must have done. Okay. Then finally he must have given these definitions. Okay. So if you see this research paper written by code, if you see this, I have this paper. If you want, I can give it to you. But all the gate relevant sections, every gate relevant part, I have already taken a screenshot and I've already put in these lecture notes. So when you read the lecture notes, already all the gate relevant, I can say portion you will be reading. But remember, in this paper, if you see this paper, I will send it to you. Basically, in this paper, it is also written why these definitions are coming, the motivation for these definitions, like from where he is getting the idea of 2NF, from where he is getting the idea of 3NF, from where he is getting the idea of partial dependency, from where he is getting the idea of transitive dependency. Basically, these definitions, these ideas, these definitions, from where he is getting the idea. Okay, so that is also given. He has written it. Like if you see the research paper, then he has written from where he is getting the idea. Okay, why he created the definition like this. Now you might be thinking, sir, why the transitive dependency definition is like this? So he has written in the research paper, but we will not go into that. Okay, we will not discuss that. In your MTech, if you take DBMS as your, if you do PhD in the DBMS, then you can do that. If you do PhD in DBMS. Okay, anyway, now let's see. So this is your another relation. I am giving you a relation R A B C D. Now consider this example that so consider this: A determines B, B determines C, C determines D. Okay, tell me here. In this, you tell me, what about this one? A determines D. Is this partial? Is this dependency partial? Tell me. Yes, ekta alpha comma beta, they can be any set of attributes. Ekta alpha comma beta, those are any set of attributes. The condition should hold. So is this partial? Is this partial? So this is full functional dependency, right? This FD is full FD. This functional dependency is full functional dependency, because you cannot remove anything from the LHS. Is this transitive? Is it transitive? A determine D. This is transitive, right? So this is not partial. You can notice this is not partial. And here this is transitive. Why this is transitive? Because you can notice A can determine D, and you can notice A can determine D, and you can put B here. The middleman you can put. So everything is picture perfect. Yes or no? Everything is picture perfect. Is this clear? Let me know. So A determining D, this is transitive. This is transitive because there is a middleman. You can put this middleman. Sandeep, this is the definition. See, this is the definition. Just apply the definition. This is the definition. Everything is written in this definition. Okay, this is the definition. Again, I am repeating that alpha determines A. Is it transitive? Here is a transitive functional dependency. Here, remember, here A is a single attribute. Here A is a single attribute. Okay, A is a single attribute. Alpha comma beta, these are set of attributes. These are set of attributes. A is a single attribute. Alpha comma beta, these are set of attributes. Also, A is not part of A. A does not belong to alpha. A does not belong to beta. Okay, is this clear? Now, this is transitive functional dependency. If this picture happens, if there is a middleman beta, if this picture happens, then we say that this is transitive functional dependency. So just apply the definition. Alpha comma beta, they can be set of attributes, but remember, beta should not imply alpha. Okay, and this A is not part of alpha. This A is not part of beta. Okay, this A is not part of alpha comma beta. So this A does not belong to alpha, and this A does not belong to B. Okay, so now after the break, we will study normal forms, which are basically 1NF, 2NF, 3NF. These things we will study. BCNF. Okay.